Okay, we're going to continue in section 2.5, section E. First we're going to talk about is average rate of change, which is basically the formula for slope. So we're going to start with this function, f of x equals 1/2 times the quantity of x minus 1 squared plus x plus, or times x plus 3. We're going to first find the average rate of change for the interval from x equals -3 to -2. So you're going to find the value of the function at -2. We're going to subtract the value of the function at -3 over the value of -2 minus -3. So the value of the function at -2, when you plug that in, you can either go to the graph and hit trace at -2 and find the value, or you can algebraically plug in the value of -2 for every x and solve. In either case, it's going to be 4.5. And when you do the same thing and put the value into the function, or go to the graph and plug in trace at -3, you get the value of 0. And that's all over 2 plus 3, -2 plus 3, which is 1. So that works out to be 4.5. When you look at the calculating from x equals -2 all the way up to -1, we're going to calculate the function value at -1, subtract the function value at -2, and that's over -1 minus a -2. Again, the denominator is 1. The difference between those two units is 1. We plug in -1, you get a value of 4. When you plug in -2, it's the same value we got before of -4.5. And when you do the subtraction, you get -0.5. One more time, we're going to evaluate the function from -1 to 0. So we're going to plug in f at 0 and subtract the function's value at -1. And we're going to do that over 0 minus -1. In the denominator, again, it's 1, because there's a difference of 1 between -1 and 0. When you put in the 0 into the function, you get a value of 1.5. When you plug in -1, same as before, we get the value of 4. And when you do that subtraction, your value is -2.5. So if we're looking at this graph, again, if you wanted to graph this by thoughts of zeros, it's hitting the x-axis at 1 and -3. So that's where your zeros are. Also, if you look at those powers, power of 2 and power of 1, the degree of the entire function is a cubic function. We've already found some of the values of these. So for example, at -3, we found the value is 0. That was our 0 point. At -2, we find the y value is at 4.5, so you can plot that point. When we plugged in -1, we got a value of 4. When you plug in 0, it hits the y-axis at 1.5. And we already know the shape of our function is cubic, so it starts low, goes through that first 0, comes up to that local maximum, bounces off that graph because this is an even power. So it's going to bounce off that 0 of 1 and go up to infinity. So if we're looking at this general shape, this is a sketch of it, and we want to look at the lines and discuss what's happening. So from this value, from -3 to -2, if you literally connect those points from x equals -3 to x equals -2, the slope of this line is going to be 4.5. Notice how it's increasing quickly from -3 to -2. And then if we look at the next one, and we're looking from the values of x equals -2 to the value of x equals -1. So from -2 to -1, if we connect those points, notice that the slope of that secant line is going down. It's not going quite as steeply. It's only a slope of -0.5. So if we look at that, it is decreasing slowly from the x values of -2 to -1. We can do the same thing. I'm looking from -1 to 0. We connect to those points at x equals -1 and x equals 0. Notice the line of that is also going down. That has a negative slope, and we already calculated that to -2.5. So it's still decreasing, and it's decreasing quicker than it did before from those points of -1 to 0. We're going to skip on down to the next part. Do some more examples in class later. We're going to go to the difference quotient. And that's what we're going to really focus on in calculus. This is just the start of it. So if we're looking at the difference quotient, it represents the average rate of change between any value of x and x plus h. And the difference between those are going to be very, very close. You're going to start with a number and go a little bit closer to it, either like 0.1 or 0.01 away from the original x. Equivalently, the difference quotient represents the slope of the secant line. It's what we just graphed on the last example. So this is the formula in order to find the difference quotient. You're going to plug in the value of x plus h into our function, and subtract the value of x plugged into our function, and divide it by h, the difference between those two units. So if we're looking at this example, I'll leave that formula up there at the top so we can see it. We're going to compute the quotient difference. Remember, that is taking the value of x plus h in our function, the value of x in our function, and dividing it by h. So looking at this one, our first one, we're going to plug in x plus h into the function. So we're going to take x and square it. So we're plugging in x plus h for the x. And then we're going to take it minus 3 times x, which we're plugging in that x plus h. And we're going to add 4. From that, we are going to subtract the function. So we're going to subtract the original function. At this point, we're just going to simplify our numerator. Our numerator is going to be x plus h quantity squared. Remember, that's if you want to FOIL this together or distribute several times over, that's x squared plus 2xh plus h squared. This negative 3 is going to be distributed to both of the things in the parentheses, so negative 3x minus 3h. We still have 4. And then this negative is going to distribute to all three things in our original function. So it's minus x squared plus 3x minus 4. And this is all divided by h. So now we're just going to start simplifying our numerator. We have an x squared that can cancel with the minus x squared. We have a negative 3x and a positive 3x. Those can cancel. A positive 4 and a negative 4 can cancel. And we're left with three things in the numerator, a 2xh, an h squared, and a minus 3h. Notice that all three of these have something common, an h, an h, and an h. We can pull that out front. We're left with 2x, one of the h's, and a minus 3. And those h's again can cancel, and we're left with 2x plus h minus 3. So if we're looking at this being our difference quotient, we can use that to find the average rate of change without having to go through all those slope formulas over and over again. So if we're looking at this first interval from 0.9 all the way up to 1, notice that they're pretty close together. We're going to have x coordinate is equal to 0.9, and the difference between these, like to go from x to x plus h, was increasing it by 0.1. That's the h. So now doing that slope formula over and over, we can just now plug this into the difference quotient, which you just found down here. So we can plug in 2 times x, which is 0.9, plus h, which is 0.1, minus 3. And when you calculate that through, you get negative 1.1. If we do the same thing for the second interval, we're going from 3.1 up to, that should be a comma, to 3.2 for that interval. We're going to do the same thing where x is the first coordinate of this, which is 3.1. The difference between these is still 0.1. So to use that difference quotient, you're going to find the slope. So we're going to do 2 times the x value this time is 3.1, plus h, which we found is 0.1, and minus 3. When you do that calculation, you get 3.3. If you actually graph this function, this is a parabola. It's opening up. It's a vertex, negative b over 2a. When you plug that in, it gets negative 1.5. And then the y-coordinate at that point goes up to 1.75. You can do that calculation on your own. The place where it hits the y-axis is when you plug in x equals 0. So if you plug in zeros to this, you're going to get the y-coordinate being 4. And if you do the y-axis symmetry, or symmetry over that line of symmetry through the middle, this would reflect over here to the same coordinate of 3, 4. So this is our general shape of our parabola. And we're looking at the two values of our intervals from 0.9 to 1. If you look at that secant line and draw that in, from 0.9 all the way up to 1, between those 2 points, notice that it is a secant line of a negative slope, and we found it was negative 1.1. If you also look at the next one, going from 3.1 to 3.2, going from about here to here, we connect that. It's going upward, positive, and it's a much steeper slope because it's a 3.3 rather than a 1.1. So the first one has a negative slope going down at a constant rate, and the next one is a positive slope and is going up much taller, much faster. And that's it.